You didn't send me a picture. Yeah. Can you? Thank you. MLUSTIG. At ECS.Berkeley. No, I'm going to see both.
Does it come on your board?
It's a alias. All right, welcome. EE123 lecture. EE123 lecture 32. Woo! It's going to be awesome today. Super excited about this lab. First of all, I think we added some improvements and kind of smoothness in the lab, so I think it'll be much better, at least on. I don't know how did it go with part 1. Anybody had issues? Part 1. It's not a huge sample, but yeah, okay. So that's fantastic. So hardware issues is usually the main thing, but we also smooth out, I think, some other things in the second and third part. So we're very excited about that. A few announcements. So Lab 5 Part 2 is out. It'll be due April 21st. Okay, so next Thursday. Okay, that's when it's going to be due. Part 3 will be out this Sunday. That means that it'll be due a week from then, which is Monday. And the reason of this really tight schedule, first of all, there's supposed to be like one lab. We're just releasing it in parts because we are fixing them. Not fixing, but like improving. So 425, that lets you do the last lab. So there's a Monday lab bash that you could use in order to iron the last kinks. And then checkoffs start immediately, Tuesday and Thursday. But by 425, you'll have a full functioning modem with some application that you'll be able to use for your projects. Okay? So that puts you within good schedule for the project. And then you can start experimentation and so on and so forth. Okay? Midterms is graded. It's not, look, we haven't assigned grades to it. So we built all the rubrics, but we haven't decided again. And I apologize for this. Again, we put more effort right now on getting the lab out as opposed to doing this. But it will be posted this weekend. The TAs did their job. I'm slacking. I've been working on that. Okay, so a few things about projects. So what I want you to do is the next time we meet with us to prepare 2-3 slides on the project. So for every meeting that you have, please make and build upon them. So again, you'll have some background in the slides. So start building basically your final presentation. Okay, so again, that will help you because you'll have figures, you'll have stuff going on, you'll have results, you'll have progress. You show improvements. Okay, so that will help us evaluate your project very well. Okay, so if you're putting a lot of effort, we'll definitely be able to see that, and that's important. Slides should show the progress, preliminary results, experimentation, and to-dos for the next meeting. Okay, what you were thinking of doing, and then we can discuss this. We don't have a lot of time, especially in my slots. There's kind of 12-minute slots, but so that's why it's really, really important that you go over it, like you make this, so we can discuss that, and so you'll be able to move on. I had office hours yesterday that nobody showed up, for example. So, yeah, it's more dedicated to the 225, but again, they didn't show up. So I was working on your lab, which was also useful. But try to use as much exposure time as you have with us, both mine, John, and Frank's. Okay? And also the lab assistants, they're very, very useful. They've done that before. And so they have some experience in how to do that, too. Any questions? So on, when was it? Like Wednesday was? On Wednesday, we went out to do the demo for the ISS. And it was sweet. It was so awesome. The ISS went by. We picked it up even with a rubber ducky. I think they were just using a high-powered transmitter, so we were able to pick them up. No problem whatsoever. The images were nice, sweet, and it was, I think, a nice experience. So I think that event is done, so they're not going to be transmitting ISS SSTV images anymore, which was, I think, perfect timing for this class. But they still have the packet transmitter up. So if anybody, once you have the modem, wants to do relay packets through the ISS, please feel free to do so. I'm not going to prevent you. And I'm going to put two Yagi antenna, the one that the measure tape Yagis, I'm going to put them in the ham shack. You should have access to it, I think. Yeah. And try to, like, whenever there's a pass, feel free to bounce off to the ISS. Okay. One more thing about the schedule. So next week, Monday, we have Laura Waller going to speak to us. And on Friday next week, we have Balint Sieber, who's an SDR evangelist, going to talk to us about hacking the wireless world. It has the nice video that he put about different application of software-defined radios. But he's been involved in a lot of things, and recently more in security, so I hope that we'll talk there about the DEN. I will not be next Friday, but please, especially for guest lecture, please make sure to come. We put an effort to bring him over here for you to listen to, and it's not nice to talk in front of an empty classroom. I get used to this, but especially. I'm trying to bring Pascal Stang, who's a former colleague, but also runs the software part of the Google Loon project. So he might be able also to speak to us. And this is also a very interesting project where Google is trying to use balloons in order to bring internet to the world. Okay, so we'll see. I'll tell you more about that if that's going to happen. But I'm positive. He just had a baby, so he's a little bit busy. Okay, anything else? So today I want to talk about Lab 5, the second and third part. And these slides can also help you as reference to compare your results. And kind of if you are a little bit baffled of what's going on, then you could look at, you can use these as references. It might be helpful. But I want you to kind of go over, there's a lot of words in the lab, so it's also a teaching part, so it's not just going through, and it's like, this is the task, this is that. Please read. Okay? There's a lot of information there, and the idea there is to tie things together from the signal processing side to the next layers of engineering a whole system. Okay. All right. So the lab is all about a very old type of a modem. Okay. This is a Bell 202 modem. It's one of the original ones. It was very low bit rate. But the truth is that's not a lot of change in sense of the basic idea of what a modem is. the nice thing about this modem is that it allows to do things over audio channel and very narrow band audio channel. And so you can then transmit data over your FM radio. But everything else would basically scale when you go to higher rates and different bands or different modulation. It's same but different, slightly different, but the concepts are similar. And the nice thing here that you'll be able to hear it, you'll be able to kind of experience what is actually going on, because when we think about a modem right now, everything is kind of hidden from us, right? Like you don't hear DSL modems anymore, or you don't hear cable modems anymore. When I grew up, I had this 14400 I think bits per second modem, and you have to dial, and you kind of like hear the communication happening. But now we actually, this is completely transparent to us. I think it's going to be a good experience to just be exposed to what's going on underneath the hood. So what does AFSK 1200 do, and why is it even called AFSK? Because really it's frequency shift keying. So frequency shift keying, you encode information by switching between frequencies. And this is binary frequency shift keying, so just two frequencies. So it encodes digital data at 1200 bits per second. So it's a slow rate. Okay, it's a slow rate, even for a channel that is meant for FM radio. So over it, effectively a 12 kilohertz channel that you're transmitting in RF, the audio bandwidth is really just 3 kilohertz. The nice thing about AFSK is that it is not a baseband. So you don't switch frequency about a baseband. You switch frequency that are a little bit modulated. Okay, and they're going to be FM modulated afterwards. Don't forget that. So it's not that we're telling the radio, we're not putting like DC bias on the radio that will switch its frequencies. Okay, that will be the best way of actually doing things. Putting DC bias on the radio, then it will switch between two frequencies in the RF. But that's not what's happening here. Okay, what's happening here is that we're putting audio frequency that has tones at two different frequencies. You see that? Note that difference, and this is why it's called AFSK. And the reason that people have used this is it allows you. So most transceivers that are meant for voice, they have a bandpass filter. They actually don't pass DC, and so that allows you to go still through a regular voice type of radio and still do digital communication. It comes at a loss because now you're less efficient. Your AFSK is being F frequency modulated afterwards, so the rates are limited to what you can do. Okay? Normally on a 10 or 15 kilohertz channel, you'll be able to transmit much faster rates, like 96,600, for example. So almost 10 times. But what they do here is that it's kind of like a system, like it's using systems that already exist. And so for those, you have some reduced capacity, but still, you can still do it because there's so many radios like that. And so that was the motivation. So this is within the bandwidth of the input bypass bandpass filter of your radio. It's actually still very popular, especially on the 2-meter band, because many people have FM radios. There's more, by the way, there's more digital radios you can start buying, and there's more repeaters being already digital, and so there the rates are much more significant, they're more automatic. But again, things were going to be slowly hidden from you in the future. So the idea there is that you switch between two frequencies. The center frequency is 1.7 kilohertz, and a delta of 500 to each side. So the signal, it really looks like this. It's a cosine or a sine or whatever the phase is, so arbitrary phase. 2 pi fc, which is 1700, times t, plus 2 pi delta f, which is 500, and then you integrate over a signal which we called, so m of tau, which is called an NRZ, non-return to zero, which are really plus minus 1 digital information at a constant bit rate, and you integrate over that. Now, what's interesting about here is that because of the choice of 1200 and 2200 and this particular bit rate, the phase at the beginning of each bit is not the same. So if you think of, how would I encode, digital modulation, I would go and I would put maybe once, some cycles of phase through one bit cycle at one frequency, and then again maybe a full cycle of phase at the other frequency. But because of the choice of the bit rate, then you can't really finish you don't finish in a full cycle of phase. And so you have to be careful when you encode this to still have continuous phase. You cannot just say, I'm going to send data at that frequency for that amount of time, and then switch and start from 0 phase again at frequency at another time. Because then the phase will be discontinuous. Okay? So the way to encode this, and I think this is a poor choice, because if they would have picked 2400, it would have been nice. But they picked 2200. Okay? So for that case, then you have to use this as a continuous phase, because if you take the derivative of that, you'll get FC plus 2 pi FC, right? The derivative of this will be 2 pi FC plus 2 pi delta F times M. So it's plus minus again, but because we integrate over the phase, then it has to be continuous. That means that every bit will start at a different phase. So the detection cannot be coherent. It cannot be locked to the phase. Okay, so for the spectrum to be narrow, we need continuous phase. The NRZ signal, which we call it NRZ, non-return to 0, is either 1 or minus 1 for a duration of 1 bit. And if it's 1200 bits per second, then it's 1 bit will be 1 over 1200. Okay, that's the duration. And depending on your sampling rate, that will have a certain number of samples associated with it. Okay? So we encoded this, and so the frequency is the derivative of the phase. It's 2 pi FC plus 2 pi delta F MT, which makes sense. But you'll have to build it that way. You cannot just concatenate pieces of frequencies, one after the other, because they'll have this continuous phase, okay? Which will be terrible for the, yep. Because that's double the frequency, so you can make sure that if you have a certain number of samples, certain number of cycles at the 1200 is guaranteed to end at 0 at the 2400, right? Yeah. I don't know why they chose it, really. I think it's a poor choice, but because you use it, so the detection then cannot be coherent with each bit. So what you're going to see is we're going to demodulate by a non-coherent. So we're going to ignore the phase when we do the demodulation. We're going to demodulate by cosine and a sine, or effectively by e to the 2 pi j, and then look at the magnitude of the result. And so that costs you also a little bit in signal to noise, too, because you cannot separate between, like, whatever is demodulated to the sine, and we'll have some noise to it, and cosine will have some noise to it. So that's what it is. Okay. So the spectrum of AFSK is actually hard to derive exactly, but when delta F is much bigger than the bit rate, then it looks like that. Okay, so 2 frequencies. The truth is that for AFSK 1200, that's not the case. The bit rate is actually higher than the distance between those two, so it doesn't look exactly like this when you look at the spectrum. Actually, the spectrum has a lot of stuff between them because of that. Okay? But what you'll do, part of the lab, is actually look at that spectrum. Okay, so you're going to write a modulator. And the modulator, it's called, you're going to write this function. The function will take bits, and we chose to use a bit array type in Python. Okay, so you'll have to use that one. And the reason that you have to use that one because our decoder for AX.25 that we're going to use later uses that type. And so it's useful just to be consistent. So you're going to take bits of ones and zeros, and then you're going to convert them into an NRZ signal of plus minus plus 1. Okay? And then do AFSK modulation, and evaluate it at a particular sampling rate. Okay, so this is a general function that you can pick any sampling rate and number of bits, but the baud, that's another term for the bit rate, baud, will be 1200. Okay? And the thing is, if the frequency that you choose for sampling does not divide with 1200, then there is a fractional number of bits within fractional number of samples within a symbol. And so you have to be careful there when you construct it. Because if you just take, let's say, if you just take the nearest value, right, and you do it over and over again, you might get out of sync. So if you just do the floor or the round of whatever the value should be, then you're going to start drifting, and that could be a problem. Now, as it turns out, 48 kilohertz really divide with 1200, so it gives you nice 20 bits per 48, 40 bits per symbol, 40 samples per symbol. Okay, that's 48 kilohertz. But 44.1 doesn't. Now, yes, we could have just used 48 for the entire lab. But there's a CD that someone has recorded of traffic from LA area that is used actually as a test signal for people to test how good their modem is. And that is sample at 44.1. So I want you to be general. Okay, and I think it's good to be able to work with that. So you're going to generate a function at arbitrary. Now, how do you do this? What you do is you generate the AFSK signal at a much higher sampling rate that does divide by both of them, by your sampling rate and by the bit rate. And if you do that, then after you generate, you downsample, and then you're guaranteed that there's not going to be a drift. Okay, so that's basically the idea. So that's how you're going to generate that. Okay, so it's not too hard. Any questions? Okay, so I want you to make sure that this works. So what we did is we generated our own at a few rates. We saved it. And then we even had added code in the lab that automatically downloads that file and loads it into IPython for you. And then you can generate then your own AFSK and then compare to make sure that it aligns. So that way you can guarantee that your code actually works. Okay, if you compare it against ours. And you can see here when I generated it at this rate or this rate, this rate or this rate, they all align. Right? There's no drift over time. But sometimes you don't evaluate at the peak, which is fine, because this is what sampling is. Okay? So you'll be able to validate at least that this works for you. And so then you can generate a valid AFSK 1200 no matter what bit rate no matter what sampling rate you're going to be doing. The next step is you're going to look at the spectrum. And how do we look at the spectrum? What you're going to do is you're going to generate a random set of 4096 bits. And then you're going to compute the average power spectrum. And we want you to compute the average power spectrum at a 10 hertz resolution. Okay? So, and as you can see, the average power spectrum should look something like this. Yes, it's concentrated around 1200. It's concentrated about 2400. But there's lots more energy in between them. Okay, because it switches back and forth between them. And there's actually some information that also leaks here, if you can see. Right? So it's not perfect. Okay. All right. So then comes the part of the demodulation. And this we improved quite a bit over last year. Can you hold on a second? I can still talk. Here's how. What we did. Did you hear me? Oh, you didn't hear the. I was weak. Sorry. Okay. So here's we added some improvements over last time to make it a little bit more robust. We looked at practical implementation that people have done over in the community, and there's always this trick of the trade of small things and parameter tuning, and there's a really nice paper actually by a faculty from Tel Aviv University, it turns out, that wrote a nice paper about high performance APRS receiver, and he had some really nice information. It's a really nice read. He doesn't do DSP, and so it's interesting how he describes that, and so it's really written for the broad public. So I think it's nice. And then there's Direwolf. It's a really nice package for an APRS software, so software modem. That they also went and optimized all the parameters for this particular CDs, to try to be able to decode as many packets as possible. Okay, and basically they win all the hardware-based implementation by a factor of 2, almost, in terms of how many packets they're able to decode. So it's really much better performance now than it used to be. So we base this implementation on their experience and some of the parameters that they've optimized for. Okay, so the idea is, first of all, AFSK is really digital FM. It's really frequency modulation. And you could do frequency demodulation, like take the derivative, basically do the same thing that we did for FM radio. And that would work fine, but as it turns out, it is, again, not as robust than the match filter approach we're going to actually use here. So there's many ways to demodulate, but let's say you did FM demodulation, and in the middle of the bandwidth you had like a small interference. Okay? That would mess up the FM. If you had like an interference here that was constant in the middle, it would just mess up the FM. Because FM is a nonlinear demodulation, and it would just not work well. But the modem that we're going to implement is going to be robust to this, quite robust to it. Okay? So here's how it's done. You get the signal in, and you do an optional bandpass filter between 900 to 2500. So it covers the bandwidth of AFSK. Now, if you just had random Gaussian noise, you wouldn't really need this. But since noise is not really necessarily random Gaussian, there can be other interferences. Turns out that this is still useful, and if not, then it doesn't do anything. Okay, so it's just maybe you burn a little bit cycles. But it does improve the robustness, so it adds more detection of a few packets that were not detected without that. Okay? So optional. But this optional thing can also then be used to optionally downsample to do that to do the detection at a lower rate, especially if you're doing it on a Raspberry Pi, okay, where you don't have a lot of computation, okay, or a weak computer or an embedded one. So then you really have to do this bandpass filtering anyway. Okay. So then what it goes through a match filtering. Now, what's a match filtering? We know that we transmitted a pure frequency for a particular bit length. So what we're going to do is we're going to convolve it with a frequency at that length. Now, you could just do with a rect window at exactly the same width, but what we're going to do is we're going to do a time bandwidth 2, so extend it to 2-bit length, but then window it. Okay, so it's kind of like a match filter. Really what it is it's got a very narrow bandpass filter at twice the bit length that is convolving at 1200 and 2200. Then you're going to take the absolute value of that. So it really gives you an envelope detection. So if there is a frequency there, I mean, we kind of did that for the GSM lab, right? We filtered at a particular frequency and then did an absolute value to detect where things are happening. This is kind of what we're doing right now. And remember, even then, we use the filter to be the size of the of the pulse because we don't want it to leak, right? So it's kind of like a match filter again. Filter the similar size as the packet length. We're going to take the absolute value. And so whenever this is active, this is going to be a positive value. And it's going to be a really low value when this is not active. And when this is active, this is going to be a high value, but it's going to be low value when this is not active. And they should alternate from each other. And when you take the difference between them, you're going to see a signal that alternates between being positive and being negative. This is, you get your NRZ signal, effectively. I call it analog NRZ because it's not going to be plus minus 1. It's going to be varying because of noise, but it's going to be positive and negative. If you would take the signum of it, the sign of it, then it would be really a pure NRZ. Okay? So this is what you have here. Now, there's an optional low-pass filtering operation that you can apply here at 1200. Now, this is low-pass. These are bandpass, and this is a low-pass. The reason that this is a low-pass, because now when you take the absolute value, everything is in the baseband. This is the envelope, right? So everything goes down to close to DC. This is the envelope. It loses the carrier when you take the absolute value. When you do low-pass, bandpass, and then absolute value, then you're just having signal that switches between -1 and 1. It's not two frequencies that switches between them. Okay? So we're low-passing at a rate which the bits come in. And again, this is optional, but as it turns out, it does improve, again, the detection. And what we're going to do is we're not going to do exactly 1200. We're going to give it a little bit of a more width, because really it's a balance between rejecting noise and keeping all your signal. So we're going to give it a little bit more, so I think 1.2 times 1200. And how this was optimized, basically on doing a lot of packets and see what's best, from a real-world type perspective. Okay. So we're actually going to implement this. In the first part, we're not going to implement this, but when you actually do the modem, I do recommend to do that. Add that. Okay. All right. So then you do this optional low-pass filter, and then you compute the sign. Okay, so now it's an NRZ signal. It goes from -1 to 1, -1 to 1, right? And it switches. And what I need to do then is sample, because I need to get my bits out. And where do I sample? I need to sample in the middle of my bit length, because that's when you do the match filtering. That's where the maximum happens, okay? In the middle. If you don't sample in the middle, you're going to be compromising your signal-to-noise ratio, because you're going to have a lower value, and so noise can throw you off to be negative. But in the middle, that's the best one. Okay? So we have to sample in the middle of the bit length, okay, all the time. And then will give me my y of n, which will be a binary signal of 0 and 1. I can convert this plus minus 1 into bits again. Okay? So that's the modem. Now, what we didn't have last year, and we have this, is another part which does timing recovery. The thing is, when somebody sends you packets, you don't know when it starts. You're just collecting data. And how do you know even how to lock into the beginning of a sample, of a packet? You really need to be able to lock. Okay? And so we added this component of timing recovery using a simple, what's called a phase lock loop. Basically, it finds the right timings. And I'm going to give you, so this is it's not really covered in the class, but this is kind of an essential thing that you do in communication. I think it's worth knowing. If you're interested, you should take, so this is control theory is related to this. It's related in communication theory. So there's a lot of work people do for this timing recovery. But I'm just going to give you a little bit from the practical point of view how to do that. And there's a really elegant implementation that I thought was like, oh man, it's really so cool. We'll just add it in. Also, might make the thing more robust. Yeah.
Okay, so when you have that signal, let's say that has 2200,
Yep.
the frequency of 2200, and then you take the absolute value.
Yep.
What's the new frequency?
So you take. So it depends. Like if there's no signal here.
No, there is.
Well, it depends. Like what's the bit rate, right? So the bits can change at a rate of 1200, right? And that's why the frequency after that will be 1200. Because the envelope changes at a rate of 1200. This is an envelope detector, right? So when I talk about bandpass filter, first of all, it's a complex single-sided bandpass filter. Okay, so it's a complex. You only get one side because we really want to get the envelope. Okay, very similar to what we did in the GSM to lock. Okay, so whenever this is active, then you'll get a peak. And whenever this is not active, this will be active. And they're going to switch between each other at a rate of 1200. And because the rate is 1200, then that will be a good filter. Now, we're supposed to see something which is really square, but after this filtering here, it's not going to be square. It's going to be more smooth. So it's, again, a trade-off between noise rejection and keeping the signal. Okay, if you have square, that has higher harmonics, right? Okay. So this is the idea. And so what you're going to do is you're going to design the slow-pass filters around 12 and, low-pass filters and also bandpass filter around 12 and 22, and then compute the envelopes. So this would be the result at this point, here and here. I'm overlaying the result, right? It's pretty cool. The mark, which is the 1200, and a space, which is the 2200, they switch between each other. And so if I sample exactly at the right points, then I would get the right bit value. Okay? Because one of them is going to be more dominant. It's pretty cool, actually, how it shows. Because this is a random set of bits. So if you have mark, space, space, mark, space, mark, it's a random set of bits. So the narrow one is really a 1-bit length, right? But these are a few bits. They're transmitted the same one. Okay. So this is the result of that part here. Then you're going to compute the difference and then have an optional low-pass filter and then take the sign. And the result of that would be this. This is the NRZ output. It switches between... Oh, I made a mistake. I'm sorry. This is not the right one. Anyway, I made a mistake in the graph. This should have been sweeping between -1 and 1. Okay, but +1 and -1. Anyway, I apologize for that. And then when you take the sign and sample exactly at the bit length, at the middle of the bit, then you get the values of plus minus ones. Now you're going to do that, and you'll have to accommodate for filter delays, how much they're delayed, in order to figure out where the sampling is. You're going to encode, and then look, demodulate, and then look, and then compare the result of whatever the output to the input. First, you're going to do that not within a function. You're going to do it you know exactly where it's supposed to start. And just make sure that these things work. And you should actually look and debug, make sure that it samples at the right place. So you compensate for the right delays for the filters, and also get to the middle of a bit. Okay? Any questions? And then you're going to display these kind of curves where you overlay the NRZ and a stem plot. So you can see that they're sampling at the right positions. And that's easy at 4800. It's a little bit more complicated, 44.1, because it doesn't happen exactly, so you have to make sure that you have something that accumulates at a certain rate, and then it doesn't drift. And again, you do that by computing something at a higher rate, and then just making sure that it works. Okay, so you have to think about a little bit about this. Okay, the next thing you're going to look at is what happens when you add noise. When you add noise, then your NRZ signal is going to look like that. Okay, so this is with noise. And you can see why digital communication is so robust. Digital communication is so robust is because even though we have this huge distortions of our signal, which analog signals would have really cost a lot, you still have the nice transition here between being positive and negative. You have this gap of resiliency. And so this is 1, this is minus 1, 1, 1, minus 1, minus 1, minus 1, 1, 1, 1. And as long as it doesn't, this one would, within the noise margin, doesn't switch to the other side, then you're good. You'll get a good rate, like you get a good recovery. And this is what's nice about digital communication. If it goes through, it's perfect. Okay? Up to a certain level of noise margin. So what you're going to do is you're going to simulate noisy data with Gaussian noise. You're going to add Gaussian noise. It's quite significant. And you're going to run for 10,000 long bit stream. And you can compute it. This is the beginning. And here, as it turns out, there's no errors. But because there's noise, there's always going to be some error eventually. Okay? And the probability of error is reduced with lower noise and increased with higher noise, the probability of making an error. And so what you're going to do is you're going to compute what's called a bit error rate. And a bit error rate is the number of altered bits divided by the total number of bits. And it really gives you the probability of a bit being identified as the wrong one. So you're going to do that. And as it turns out, you should get, if you implement it correctly, about a bit error rate of 0.0012. So one of every 1,000 of, every 1,000 bits will be erroneously detected. Okay? Something like that. If it's much higher than this, means that you're not doing something right. If it's much lower than this, then good job. But you might also not be doing something right. So be happy, but validate. Okay. It should be in that order, though. Okay. All right. So this is for a particular case of adding a certain Gaussian noise with standard deviation of 1. Okay. Then what you're going to do is you're going to compute empirical bit error rate curves. So now you're going to simulate adding more noise or different noise level, and basically, this curve shows here different noise levels. So here is very little noise, and here is very low noise. And this is the bit error rate, and it's a log-log curve. And you can see that when the noise becomes significant, you're getting a bit error rate of half. It means that you have no information. You don't know if the bit is right or not. Like it's always, it's 50%. It's like flipping a coin. You could just flip a coin and not receive anything, pretty much. And here it's a good situation. And I gave you now our analysis, and you can load it again in the same way and compare. And this, you have a graph generating Mickey's, and this is going to be yours. And of course, it's going to be slightly different because it's random choice, right? So it's going to be slightly different, but it should follow approximately the same. Now remember, this is log. So if it starts here, this is not, if it starts here, it's not good. Okay? So it needs to be really close to this. Okay? Any questions? Running out of time. I really want to move on. Okay. So timing recovery really tells you where to sample. Okay? And so what you're going to implement is a very simple phase lock loop. And here's the idea. The idea here is that we need to know where to sample. So we're going to have a counter. We're going to have a counter which I call PLL, and it's 32 bits. And what I'm going to do then, ignore this part. This counter, if this part doesn't exist, this counter is just going to add 2 to the power of 32 divided by Fs over baud, which basically this is the number of samples per symbol. And it's just going to add 2 to the power 32 divided by the number of samples. So every time it's just going to advance by a certain rate. When it overflows, that means that now it's time to sample. Okay, so the counter, when you add this constant. So every 40 samples, it is going to overflow. Okay, and go from being positive to negative. And so whenever this is overflowing, then you know that this is the time that you need to sample. Okay, so if you start in the right value, then this would always produce an overflow when you need to sample. Every 40 samples at 48 kilohertz. Okay? The nice thing about this, it works even at 41.1 kilohertz, because then you just need to take 41 here, and it will produce you exactly when you need to sample. So that's cool. Now, where's the locking part? The locking part is that we want to shift this counter when it's not synced to my signal. So I want to shift it. How do I do that? I take my signal, my NRZ signal, and then what I do, if my counter is locked to my signal, they're going to have, whenever the NRZ has a zero crossing, whenever it switches between 2 bits, then my counter should also cross 0. Okay, they should cross 0 at the same time. How do I make sure they cross 0 at the same time? I check, is this crossing 0? If it is, what I'm going to do then is I'm going to take my counter and I'm going to nudge it. I'm going to nudge it towards 0. So if my counter is not 0 and the 0 crossing happens here, I'm going to nudge it a little bit towards 0, multiplied by an A, which is between 0 and 1. Just nudge it a little bit. So if it's not synced, then it's going to nudge it. And then the next time there's going to be a 0 crossing, it's going to nudge it again, till they fit. When they fit, then you don't nudge it anymore. Multiplying by an A of 0 times 0, it does nothing. Okay? So that's a really nice idea, I thought. Yeah. Okay, you could reset it to 0, right? And that's going to be a trade-off, but this, remember, is noisy. So if I reset to 0, then it's completely going to lock to this, also to the noise. So it's always a balance between sensitivity to noise. You know that the sampling rate is every 40 samples at 48 kilohertz, right? But sometimes, you don't know where it starts. And so you want to be able to sync. And so if I just nudge it, it's still going to have a certain rate that fits. On average, it's not going to move. It's kind of like filtering. And actually, you can show it. Here's an example of this is the signal comes in. And when I'm not locked, you see that the 0 crossing here is not locked to it. But then as you move away, it starts getting locked, and now it's better, now it's perfect, almost perfect because of noise, perfect, so it starts locking to it, yeah.
Why do we use overflow as opposed to just numbers?
It's just a really simple implementation. We do that in C, right? So it's basically you don't need to do ifs, right, so much. If it changes, you don't have to check so much. If it changes sign, then you know that to check. It's just a nice way of doing. Instead of mod, you can do mod too. Something that is cyclic, pretty much.
If it's a negative number, though, and we just multiply by A, aren't they actually nudging it?
It still nudges it to the right position. That's the nice thing about it. If it's negative, it still nudges it towards 0. Right? So that's another thing for stability. But this is a IIR filter. If you think about it, it's nonlinear, but it's kind of like an IIR filter. If you think about this. So the idea is that it minimizes basically the counter at n minus m of n for 0 crossings of m of n. So it's only for different places. It minimizes this difference. Okay, when this is 0 crossing, then it minimizes that difference. This is what it tries to optimize. And basically, if the sign of that equals to the sign of the previous sample, then I'm going to take 1 minus, for example, 25. So it would be A equal 0.75 of the previous counter, plus the delta counter. If this happens over and over and over again, right, then I can remove this if statement here, And basically my system is going to be C of n equals 0.75 C of n minus 1 plus delta C, which has a transfer function of something that decays over time, right? So effectively my timer will lock to 0. Right? That's what it does. It shrinks my timer all the time to 0. And if it's not, then my timer just keeps on going. Now what you're going to do is you're going to see how it locks. So if you pick A equals 0.75, and these are packets that starts randomly, then you see that first it doesn't sample at the peak, but then it locks, and then keeps on sampling at the peaks. And then new packet comes in, and it takes time. But this one, it was pretty quick. This one, it takes a little bit longer, but because of the right timing. But then eventually, after 5 bits, it locks, and so on and so forth. If you pick A equals 0.9, so now you don't nudge it so much, it will take more time to lock. Now, what's the trade-off? The trade-off, of course, is time to lock and the jitter, right? So if A is 0.95, then, my sampling rate is always going to be around 40, maybe plus minus 1. But I'm going to be really good, I have a good clock. I'm sampling at the right rate. But it will take time to lock. For 0.75, it starts jittering a little bit because of the signal that comes in, if it's noisy. And if for 0.4, it's really going to just do whatever the signal almost tells it. And so it's going to really jitter with noise. And so it's really a balance. So what we're going to pick is something like that. Okay? I'm going to steal a couple of minutes because I want you also I want to cover a little bit. So I'm going to steal 3 more minutes if that's okay. So the next part really is implementing AX is what you did here is implement a physical layer. So if you think of a network or the OSI model for networks, you implement really a physical layer. It has the modulation, has the signal, has the medium, radio. The next one is a data link layer that you puts that data into packets that allows you to have some addressing, and error correction and things like that. Okay, so this part you're going to be implementing next. And so the lab implement will basically a packet-based transceiver, send receive packet to other classmates, and send receive to APRS packets that you can interact with other APRS receivers in the Berkeley area. And that will be distributed and also aggregated to the internet, which is cool. X.25 is a link layer packet-based protocol used by ham radio based on the X.25. A is for amateur. This is the packet structure. Has a flag, destination address, source address, distributing. So this is repeater address, control field, ID, information field. That's where the data is. And then this is checksum to check for error. And then a flag at the end. So it always starts with a flag, end with a flag. There's a few details here. It's encoded not in NRZ. It's encoded in NRZI. Non-return to 0 inverted. That means that a 0 bit is encoded in a change between mark and space. And a 1 bit is encoded by no change. So if you're mark, that means it's a 1. If you mark space, that means it's a 0. If you're space mark, that means it's a 0 too. Okay? So a bit stream of zeros will just alternate between mark and space. So this thing is converted to this. Now, it wants to guarantee that there's always changes every once in a while because you want to be able to lock to these zero crossings. And so it does bit stuffing. So every 5 bits of 1s, it will then stuff your sequence with another 0.